Lesson 4-4, Graphing a Function Rule. All right, so we've been talking a lot about these function rules for linear and nonlinear functions. So today we're just going to talk about how to create these graphs. All right, so if I scroll down a little bit, essential understanding. The set of solutions of an equation forms that graph. So when we graph, we're graphing all of the solutions to that function or equation. A graph may also include solutions that do not appear in a table. So you could connect, if you have a couple dots plotted and you continue that line, you can be showing solutions that maybe you didn't get on your table. If you're graphing something for like a real world situation, you want to make sure you're only showing points that make sense. And we're going to talk a little bit about that. Okay, so first of all, problem 1, graphing a function rule. They're going to give you the function. Step 1 always is to make a table. So I kind of make a 3-column table. The function goes in the middle, your x's or your domains are on the left, and your y's are on the right. They decided to write them as ordered pairs, but if you just wanted to write the y values, that would work. Oh, it looks like they have them right here. Okay, so what you do is you write your equation. You decide which inputs you want to graph. Now, it's always good to include 0, and then you always want a couple negative and a couple positive. So 4 to 5 points gets you a good graph. Because you're never sure if it's linear or nonlinear. So if it was nonlinear and it has a special curve, you want to have enough points so you can see that curve. Okay, so they picked these points. These are chosen by you. You plug them in to the function and you get your output. Plug your next one in and you get your output. Next one, output, next one, output. So now I have my points, my x and my y values. I take it right over to my graph, -1, -1, +3, there it is. Plot all my points. Connect the points with a line so that you can represent all the solutions, because there could be solutions in between those points you graphed. Okay, so it's pretty simple. I'll just show you one more. Here's the function. They would like me to graph it. I'm going to put that in the middle column of my table. Now I'm going to pick some x values. I'm going to say -2, -1, 0, and 2. Plugging that in, 1/2 times -2 minus 1. Well, that's a -1 minus 1 is -2 for my y. Plug in a -1. -1 times 1/2 is -1/2. Minus 1 is -1 and 1/2. Plug 0 in, that's an always easy one. This is equal 0 minus 1. And 1/2 times 2 is 1 minus 1 is 0. Then you want to plot these points. So I'm looking at my x and y. -2, -2. -1, -1 and 1/2. 0, -1. 2, 0. So it looks like they all line up, and I just connect them with a line and arrows, always arrows. Okay, so easy as that. Now, if you're graphing a real-world function rule, remember to choose appropriate intervals for the units on your XY axis, and also think about what numbers are appropriate for your input values, your x's. So in this example, the function rule W equals 146 times C plus 30,000 represents the total weight in pounds of a concrete mixer truck that carries C cubic feet of concrete. So C is our input. Now, the capacity of this truck is about 200 cubic feet. So what is a reasonable graph of the function rule? Okay, so I have my xy. My function is 146 times C plus 30,000. I need to think of appropriate x values. So I don't want to start plugging in -3, -2. You have to think, will we use positive and negative numbers? If I'm talking about cement that's going in a truck, we don't have negative cement. So 0 would probably be my minimum. If there was 0 cement in the truck, how much would it weigh? That's what I'm solving for y, the weight. All right, well then what's my max? Well, the truck can only carry about 200. So I can choose numbers between 0 and 200. So I'm going to count by 50s. So now I'll plug these in and I'll get my y values. They've done it for us. So they use the same inputs, 0 through 200, and they got their outputs. So these are the points that you would then graph on your graph. Okay, so this is an appropriate graph for that scenario. Now, will we connect the lines on the graph? In a real life situation, you have to think about this. Okay, this brings us to continuous graph and discrete graphs. Continuous graph is a graph that is unbroken, solid line. Discrete graph is composed of distinct, isolated points. We don't connect them. Now, there's a reason we use these two. Going back to my concrete mixer problem, I'm going to connect these points because I can measure the weight of that truck with any amount of concrete in it. So I'm going to fill the line in so that I could find solutions for all of these points. Now, let's look at a different problem. In this problem, so we're going to think about if it's continuous or discrete. It's another real life problem. The weight W of cheese in ounces depends on the number of gallons of milk. So here's the function. W weight equals 16 times M. The second scenario, the amount of money made from selling cheese depends on the number of wheels. So there's that function. Okay, so they're going to have us make a table. Well, they did that for us. If I put 0 pounds of milk, I've made 0 cheese. If I put 1 pound of milk, I've made 16 ounces of cheese, and so on and so forth. If I sell 1 wheel of cheese, I make $9. If I sell 2 wheels, I make $18. Okay, so that's how we interpret our two tables. We don't want to use any negative numbers in this situation because we can't have negative milk and we can't sell negative wheels of cheese. So notice they started at 0 and went on. Now, are we going to connect the points of these graphs? Well, can I find the weight of this cheese with any given amount of milk? Yes. Okay, so I could find out how much the weight is if I had 1 3/4 cup, something in between 1 and 2. So this would be a continuous graph. However, if I'm only selling whole wheels of cheese, I can't find a price for in between that amount. So this would be a discrete graph because I'm measuring whole wheels of cheese. So the graphs would look like this. Continuous for weight, and money earned would be discrete. Let's look at some more examples. In example A, the amount of water in a wading pool in gallons depends on the amount of time that the wading pool has been filling. Okay, if I were to graph this, so I kind of think of it like in the summertime when you have those little inflatable pools and you put the hose in to fill it up with water. I can measure the volume of this pool at any given time. So there's not really discrete measuring points. So this would be a continuous graph for how much water is in my pool. In example B, the cost for baseball tickets in dollars depends on the number of tickets bought. Well, since I can't sell half tickets, this would be a discrete graph. I would not fill in my line. Okay? And our final example is graphing nonlinear functions. So you do this the exact same way as you do linear. They give you the function, make it in a 3-chart table with your function in the middle. You choose the x values. Remember to do negatives, 0, and positive numbers. You find your outputs, and then you're able to graph. So this one created a V. All right, so that brings us to our lesson check. I'd like you to, let's see, actually, I'm going to have you graph 1, so you're graphing the function rule. 1, this is a linear. 4, this is a nonlinear. I know that because there's an exponent. And then 5 is a real life situation. So I'd like you to make a table and graph it, thinking about what inputs are reasonable. So just 1, 4, and 5, and bring these to class. Remember to make your table, pick your inputs, and you'll find your outputs.